So, welcome to all of you on this 11th day of our course. I hope you are learning, and today you will learn several things about linear algebra topics. So, it is very important part of mathematics. Very, very important. Very, very interesting. So, in matrices or in linear algebra, we studied some basics like matrices, matrix operations, transpose, determinant, inverse of a matrix. So such things uh, we studied. So today I'm going to start with first the solution of system of linear equations. Okay. So first you must understand what is a linear equation. So a linear equation, if it is in three variables, it is like this: ax plus by plus cz equal to d. A, B, C, D, these are scalars, numbers. Okay. X, Y, Z are variables. Suppose linear equation is in two variables, it will be like this: ax plus by equal to c. Okay. So linear equations means variables will not be multiplied. Their degree of each variable will be one. Okay. So this is a linear equation. But we are talking about system of linear equations. So if we have more than one linear equation, okay, then it is system of linear equation like this. You can see that here you have two equations in two variables. So this is system of linear equations in two variables. And you can see that this is system of three equations. Okay, in three variables, this is system of three equations, three linear equations. So if you have more than one equation, then this means you have system of equations, and these are, if those equations are linear, then you say that you have system of linear equations. Now we have to talk about the solution of such system, but before that it is categorized into two parts. If we look at this in two variable system, linear system of linear equation, you have here coefficient constants c1 and c2. If both of these are zero, if c1 and c2 are zero, then the system is called as homogeneous. Then you have homogeneous linear equations. Okay, and system is homogeneous. Otherwise, it is called as non-homogeneous. Similarly, in case of three variables, if you have these constant d1, d2, d3, these are all zeros, then it is system is homogeneous. Otherwise, it is non-homogeneous. It is just similar to that you studied in differential equations. There also the differential equations were categorized in homogeneous and non-homogeneous. So here you have also the concept of homogeneous and non-homogeneous. It depends on this right side coefficients. These are zeros, all zeros or not. Okay. But if we talk about the solution, so what does it mean by the solution of a system of linear equations? So solutions mean the values of those variables that will satisfy the given system of equations. If I'm taking this system of three equations, then I need to find the values of the variables x, y, and z so that all these will be satisfied by those values of x, y, z. Okay, so we have to find the solution that will satisfy this system of linear equations. Okay, or there may not be a solution. So we will check all the conditions whether the solution exists or not. If it exists, then what is that solution? So actually a system of linear equations may have unique solution, infinite solution, or no solution. There are three possibilities. Okay. So if the solution exists, whether it is unique or infinite, the system is said to be consistent. Okay. If the solution exists, then it is said to be consistent, and solution exists means it can be unique or infinite. We will study under which condition it will be unique and when it will be infinite. We will learn that. And but if the solution does not exist, if there is no values of x, y, z such that all those equations are satisfied, then we say that the system is inconsistent. It is very important. Okay. Now, first I'm going to discuss for the solution of the system of linear equations in two variables. Okay. So for that, the simple thing is that we have method of elimination that I think many of you may be knowing about it, but I'm going to discuss that there is method of elimination if you have system of linear equations in two variables. You have this system in two equations. If you have two equations in two unknowns, then there are three possibilities. Actually, each of the equation is representing a line in the plane. You can draw the line a1x plus b1y equal to c1, and another equation also. These are actually the equations in xy plane, and these can be drawn very easily. So there are three possibilities. Either these lines will intersect like this. Suppose this is possibility one. Okay. Or these will be parallel, or these will coincide. There are three possibilities. Okay. In the first case, if these are intersecting, there is one point of intersection. So this point of intersection is lying on both. This means that this point, if this is suppose x comma y, so this point will satisfy both equation. So this means that the system has exactly one solution, unique solution. There exists unique solution in this case if both lines intersect at a point. But if lines are parallel like this, the second case, this means there is no value of x that will satisfy both the equation. There is no point which is lying on both. So this means there is no solution. Okay. So actually what we are doing, we are trying to understand this with geometrically. What happens when you have system of two equation in two unknowns. And another case is when these coincide, overlapping. Okay, so how many points are there which are lying on both? So you can see that on this line, all the points are lying on both. Means there are infinitely many points which are satisfying both. So this means that the system has infinitely many solutions. Okay, so geometrically for a system of two equations in two unknowns, we can understand about the solution like this. How to calculate for such system mathematically? How to find the solution, how to find that whether solution exists or not. So these are the conditions for this. You can check without drawing the equations. So first thing is for unique solution, you have these equations a1x a plus b1y equal to c1. I'm writing here again. You have equations a1x plus b1y equal to c1, and another is a2x plus b2y equal to c2. If to find the ratio a1 upon b2, a1 upon a2, and it is supposed not equal to b1, then we say that there is unique solution. Okay, but if a1 upon a2 is equal to b1 upon b2, but this is not equal to c1 upon c2, this means there is no solution. So in this case, no solution exists. And if all these are same, these ratios a1 upon a2, b1 upon b2, and c1 upon c2, if all these three ratios are same, then we say that the system has infinite solutions. Okay. So geometrically, you can see, and in this way also you can find the ratios and you can determine what is the possibility for solution. So you can also here understand with the help of example. If you have this system of equations, two equation and two unknowns, then in this question, here a1 is 5 and a2 is 1. So a1 upon a2 is 5 upon 1, and b1 upon b2 is 3 upon minus 2. So these are not equal. So this means that the system has unique solution. Okay. So you can determine with these conditions that which kind of solution is there or solution is there or not. But what is that solution? So you will use the method of elimination. So from these two, you can eliminate x or y, and you can find values of x and y. Do you know the method of elimination? Do you know how to solve these two equations? Because I have written directly the value of x and y. So you can solve these equations to find the values of variables x and y. Okay, Arnab, Shiva, substitution. Yes, you can substitute value of one variable from one equation and you can put that in another equation. X value in equation 2. Yes, you can do that. You can find value of x from 2 or you can put in 1 or vice versa. Yes. Okay. And such equations, if solution exists, you can also solve with the help of your scientific calculator also. Okay. Let's see the next question. If you have this system, then for this system of equation, the ratio of a1 upon a2, this is 2 by 3. b1 upon b2 is also 2 by 3. But c1 upon c2 is 4 by 11. So here these two are equal, but these two are not equal to c1 upon c2. This means this is condition of no solution. So no values of x and y will satisfy this system. Okay, so in this case there is no solution. Third one, here all ratios are equal. So this means system has infinitely many solutions. Okay. So in this way, you can determine the solution of system of equations in two unknowns. Okay, if you have two equation in two unknowns, you can determine in this way. But if you have either such system means two unknowns in two equation in two unknowns, or if you have three equations in three variables, then what to do? So then we have another method also. This is called as Cramer's rule. So according to this Cramer's rule, if you have system in two unknowns, two equation in two unknowns, then according to this method, the solution is what? X equal to d1 upon d and y is d2 upon d. So what is d1 and what is d2 and what is d? So d is basically the determinant of the coefficients. D is what? Here the coefficients are a1, b1, a2, b2. So determinant, you will find the determinant of these coefficients matrix from obtained from the coefficients. Okay, then it is D. Like suppose I take the question, this one. Okay, so if you what will be D here? D will be actually the determinant of what? The matrix, coefficient matrix. So what will be coefficient matrix here? 5, 3, 1, minus 2. So D will be the determinant of this matrix. Now what will be D1? D1 means you will replace the first column of D by this column of constants on the right hand side. So what do you have? D1 is basically 1, 8 and second column will be as it is. Okay, so in D1 you have to change only the first column and you have to find the determinant. So this will give you D1. Similarly in D2, you will change the second column of D. So first column will be as it is. Okay, and in the second column you have 1, 8. So in this way you have D, D1 and D2. So when you have values of D, D1 and D2, then you can find X. So what is X? X is D1 upon D and Y is D2 upon D. Okay, so you can check here in this question, what is D in this example? It will be minus 10 and minus 3. So minus 13. What is D1? Minus 2, minus 24. So minus 26. What is D2? 40 minus 1, 39. So what is X now? X is what? D1 upon D means um, minus X is d1 upon d. d1 is minus 26 upon d is minus 13. So it is 2. And y is d2 upon d. So what is d2? d2 is 39 and d is minus 13. So it is minus 3. Okay. So you can determine solution by using the Cramer's rule also. Okay. But in this condition, there are some conditions here also because d must be non-zero. I'll discuss that later. Okay. So if d is non-zero, if the denominator, this d determinant is non-zero, then easily you can determine your x and y by using the Cramer's rule. Okay. If d is zero, then I'll discuss the conditions. Okay. Similarly, if you have system of three equations in three unknowns, then x will be d1 upon d, y will be d2 upon d, and z will be d3 upon d. Okay. So again here d is the determinant of the matrix of coefficients. Okay. And d1 is what? d1 is obtained from d by replacing the first column with the constants on the right hand side. The only the column you can see the difference between D and D1. Second and third column is same in D and D1. Only first column is changed. Similarly, you can see the change in D and D2. So in D2, the second column is changed only. Okay, and first and third column are same as in D. Similarly, you have D3. So in D3, third column is the with written with these constant D1, D2, D3, and first and second column are same as in D. Okay, so you can determine these determinants and then find the solution by using these formulas for x, y, and z. So so let's see first this question. Here you have to solve the following system of equation using Cramer's rule. Okay, so you have given three equations in three unknowns. This is system of three equations. So first the D is to be calculated. So D is calculated from the matrix of coefficients. So what is the matrix of coefficients here? From first equation it is 5 minus 7 and 1. From second 6 minus 8 and minus 1 is there. Second row, and third row is 3, 2, minus 6. Okay, so write carefully. Suppose in any equation, suppose in equation 2, one variable is absent. Suppose this minus z is absent there. Then what will you write? You will write 0 in place of this. If any variable is absent, so its coefficient will be 0 there. So you will put 0 in place of that. Okay, keep in mind this point. Now from this matrix, you can find the determinant. So it is 55 in this case. Then D1, D2, D3 are calculated. Okay. And using the formula for x equal to D1 upon D, y equal to D2 upon D, and z equal to D3 upon D, you have values of x, y, and z. Okay. Now, see, if in case of two simultaneous linear equations in two unknowns, you know that if your D is non-zero, that I have already discussed. If D is non-zero, then you can find the solution by using these formulas. Okay, system has unique solution if D is non-zero. So okay, solution is unique, system is consistent, and values of x and y can be obtained from these formula. But what happens when D is 0? So you can see that in point 2 and 3, if D is 0, then what happens? So if D is 0, and suppose both D1 and D2 are also 0, then system is consistent and it has infinitely many solutions. Okay, but if D is 0 and one of D1 and D2 is non-zero, then system is inconsistent. Okay, means no solution. So in this way you can determine when the solution exists, when the system is consistent, or when the system is inconsistent. Okay, so Cramer's rules also help us to determine about the solution. Okay, but if you are doing with three simultaneous linear equations in three unknowns, then what happens? If D is non-zero, then the case is similar. System will be consistent. It will have unique solution, and solution is obtained by these forms. Okay. Now, see, if in case of two simultaneous linear equations in three unknowns, then what happens? If D is non-zero, then the case is similar. System will be consistent. It will have unique solution, and solution is obtained by these forms. Okay. Now, Okay, but when D is 0, so when D is 0 and D1, D2, D3 all are equal to 0, then here the system of equation may or may not be consistent. We cannot guarantee that it will be consistent. It may or may not be. Okay, but in case of two equation, it was confirmed that it is consistent. Here the system may or may not be consistent. If it is consistent, then it has infinitely many solutions. Okay. Third point is if D is 0 and at least one of the determinants D1, D2, D3 is non-zero, then the given system is inconsistent. So this third point is similar in both uh, both case 1 and case 2. Only there is, and first point is also similar, only there is difference in second point. When D is 0 and all other D's, D1, D2, D3 are 0, then it may be consistent or it may not be consistent. If consistent, then infinitely many solutions. Okay, so this is by Cramer's rule. So you can see another question also. Here you have system of three equations in three unknowns. So you can see that here all determinants D, D1, D2, D3 all are 0. So we can say that system is consistent or inconsistent. If the system is consistent, then it has infinitely many solutions. Okay, otherwise it is not consistent. Okay, so we cannot say that it is consistent. Okay, there is possibility of both. So we will also learn one method in which you will say with confirmation that it is consistent or not. Okay, but here you cannot say in this case when you have all determinants equal to 0. Okay, so this is Cramer's rule. Okay, so now you have learned about the solution of system of equations. Okay, and if you have two equations in two unknowns or three equation in three unknowns. Okay, so for two equation in two unknowns, you have elimination method, you have Cramer's rule. For three equations in three unknowns, you have Cramer's rule. Okay, so after this, I'm going to discuss another method that you will apply for three equations in three unknowns or a system having more than three unknowns and more than three equations. Okay, so before doing that, if you have any questions, please ask. Is it clear to all about this elimination method for two equations in two unknowns or for this Cramer's rule? If you have any query, so please ask. Okay. So let me save this file. Okay, so now I'll discuss Gaussian elimination method. Okay, but before that, you must know what are elementary transformations. There are two types of transformations: row operations or row transformations and column operations. So elementary operations or elementary transformations are of two types, whether we apply for row or for column. Okay, so you need to understand before Gaussian elimination these transformations, these operations, and about the rank of a matrix. How to find the rank of a matrix. If you know that, then you can apply your Gaussian elimination method. Okay. So first I'm going to discuss this elementary transformation, then I'll focus on the rank. Then we will move for the Gaussian elimination. So let's start this. So elementary transformation, there are actually three elementary transformations. The first one is the interchange of two rows or two columns. Okay, so if you have a matrix Then what you can do, the first operation that you can apply it is interchange of two rows. So suppose for this given matrix, you have to interchange row 1 and row 2. First thing is that this R1 is written, R1 means row 1. So we denote the rows by this R1, R2, R3 like this, or column by C1, C2, C3 and so on. So in this matrix, if you have to interchange R1 with R2, there are only two rows. If you have to interchange R1 with R2, so what will you write? You write like this: R1, this is sign for interchange, and with R2. Okay, so you will write like this. Now, if you will apply this operation, so what will you have? You have 3, 4, and 1. Okay, so after interchange, you have this. So if you apply elementary transformations, so then you can see that these two matrices are not equal because you have interchanged the rows. These are not equal, but these are equivalent. So you can substitute the sign of this equivalent. Okay, don't write the sign of equal to here. If you have to apply the operation of C1 interchange with C2, this means you have to interchange two columns, C1 and C2. So what will be the matrix after the applying this operation? So you have first column 2, 4 and another column 1, 3. So you have this matrix if you apply this operation interchange of C1 and C2. Similarly, you can do if you have a matrix of order 3 cross 3 having 3 rows. So now if you have to interchange R1 with R3, then what to do? So you will write the first row will become now 1, 5, 4. Second row will be as it is, and third row will be 4, 2, 3. Okay, so in this way you can interchange. Similarly, if you want to interchange, uh, just a minute. Similarly, if you want to change column C1 and C2, so C1 and C2 will be, the first column will be now 2, 4, 5, second will be 4, 1, 1, and third one will be as it is 3, 5, 4. So in this way, you can apply the operation of this interchange of two rows or two columns. Okay. Now the second operation is multiplication of a row or column by a non-zero number. Okay, but what is the requirement of this operation? You will see later when you will find rank. Okay, so if you have to multiply a row by a non-zero number like this, if you want to multiply by 2 in R1, so what will you write? R1 arrow 2R1 means you this R1 is indicating that you are going to apply the operation in R1, and what you are going to do? You are going to twice this row R1. So after this, what will you have? You have 2, 4, 3, 4. Second row will be as it is, and first row will be twice. Okay. If you have this matrix A and you want to apply this operation, means if you want that in C2 column, you want to multiply by 1 by 2. Because operation is for multiplication, right? So don't say that you are dividing by 2. This means you are multiplying by 1 by 2. Okay. So if you want to multiply by 1 by 2, so what do you have? So in second column, there will be change and another two columns will remain as it is. So the second column will become now 1, 2, 3 and third will as it is 1, 2, 3. Okay. So in this way, you can apply this operation. Now see the third operation. So what is this? It is the addition of elements of a row or column to the k times multiple of elements of another row or column. And k times this k is non-zero. So what does it mean? Suppose if in this row R2, you want to make here this element as 0. So actually what do you want? You want that in R2 you want to add 3 times of R1. means you want to apply this R2 plus 3R1. So first thing is that you want to change in R2. That is why you will write on left hand side R2. So R2 arrow means you are going to apply your operation in R2. And what you are going to do? You are going to add 3 times of R1 in R2 so that you will get here 0. Okay. Because minus 3 plus 3 into 1 is 0. So what do you have now? First row will as it is. In second row you have here 0 because R2 plus 3 R1, 3 times of 1 and minus 3 is 0. Then for this second element also, so 3 times of R1 is 6 and 4, actually this 4 plus 2 into 3 times of 2. So you have here 10. Okay, so in this way you can do. So this operation is very important. All these three are important. Okay, but and these all these are used in your when you find the rank. Okay, so in this way you can apply this operation. Similarly, you can see this in 3 cross 3 matrix. If you want to apply the operation of R2 minus 2R1 in R2, row R2, what do you want? You want here 0. So what will you do? You are applying by minus 2. Actually, see this R2 minus 2R1 means what? R2 minus 2R1 means what? R2 plus minus 2R1. Because I have written operation addition, not subtraction. Okay, so whenever you see like this, so actually this R2 minus 2R1, so actually this is what? This is R2 plus minus 2 times R1. So what are you doing actually? You are adding minus 2 times of R1 in R2. Okay, so actually I always do like this. So what to do? So in R2 you have to make it 0. So what I do in R1 multiply by minus 2 and add. Okay, so in place of subtraction, addition is easy to do. Okay, so multiply by minus 2 in R1 and then add in R2. So minus 2 plus 2 is 0. So first write first row as it is. Then you here you have 0. Now minus 2 into 2 is minus 4 and minus 4 plus 4 is 0. Then minus 2 into 4 is minus 8 and minus 8 plus 3 is minus 5. Okay. Then in third row, what you have to do? R3 minus 5 R1. Actually, this is what? R3 plus minus 5 R1. So what you have to do? You have to multiply by minus 5 in row 1 and add in R3. So minus 5 plus 5, 0. Then minus 10 plus 1, minus 9. Then minus 20 plus 2, minus 18. Okay, so if you will do like this, multiplication in R1 or R2, whatever is the row, and addition in your desired row in which you want to do change. So if you will do like this, then it will be very easy for you. Okay, so are these operations to okay to all? Vivek, Zorli, okay, Arnab. What about others? Okay, Shivai. Okay, great. Now, let's move to the rank of a matrix. So rank of a matrix is very important. It will help you when you will learn Gaussian elimination method, and it is also helpful when you study linear transformations, linear independence, dependence. So very useful concept, very important. Okay, so now first I'll discuss about the definition of a rank of a matrix. Then I'll discuss some methods to find the rank of a matrix. So what is it? So if you have a matrix of order m cross n, if that matrix has at least one non-zero minor of order r, here minor means, you know, minor, Minor means determinant of submatrix. Determinant of submatrix of a matrix. If you have at least one non-zero minor of order R and all minors of order greater than R are zero, then rank is R. So actually, what is it? Let's discuss with the help of example. See, you have a given matrix. Okay. Submatrix, Shiva, I'm telling you, you have given matrix. Okay. And you have to find its rank. So now how to find? If we want to find by using this definition, so according to that, we have to find a minor non-zero. Minor means determinant. You have to calculate determinant of what? Of submatrix. Okay. So if you are asking about some matrix, so see, first we will start with the higher order. So see, if you have this matrix A, so higher order is 3, because first thing is that we can find the determinant for a square matrix. Okay, so in this, the largest matrix, which is a square, is of order 3, the whole matrix 3. Okay, so what will you do? First, you will find its determinant. Okay, so you will see that determinant is 0 here. So this means that you have minor equal to 0. Minor of order 3 is 0. Okay, you can say that minor of order 3 is 0. Okay, then what to do? You have to check for submatrices. Okay, so you have checked for higher order means of order 3 cross 3. Now you will check for a matrix of order 2 cross 2. So you will choose submatrices. What means submatrices? You will choose like this is, you can take this matrix, this is of order 2 cross 2. You can take this matrix, this is of order 2 cross 2. Or you can take this 1 2 and 2 5. This will become a matrix of 2 cross 2. Okay, so you will check for sub matrices of order 2 cross 2. Okay, why 2 cross 2? Not why not for 1? No, first you have checked for 3 cross 3, then you will decrease the number, decrease the order. Then first you will check for order 2 cross 2. If you will find at least one sub matrix of order 2 cross 2, which will give you non-zero determinant, then rank will be 2. So in this case, I have taken some matrix this 1 2 1 4. Okay, this is giving non-zero determinant, so rank is 2. Suppose R1 C2 should not R1 C2 should not be minus 2, and what do you want to say? R1 C2, where is R1 C2? I'm not getting what you want to say, Arnav. Row 1. I'm not getting what do you want to say. So see again the definition. If A has at least one non-zero minor of order R and all the minors of order greater than R are 0. So in this example, what I want to say that if you have checked for the determinant of order 3 cross 3, because the higher order which is possible to find the determinant is 3 cross 3 here. So you can see that here determinant is 0. Okay, for order for matrix of order 3 cross it is 0. Now we will check for order 2. So I have one, at least one matrix which is giving me non-zero determinant, so the rank is 2. Okay, suppose um, again you can see in another example. Here you have matrix of 3 cross 3. The determinant is 0. So this means rank is not equal to 3. Now you will check for a matrix of order 2 cross 2. So you have at least one sub matrix which is giving you non-zero determinant. So again the rank is here 2. Suppose in this matrix I make some changes. Suppose it is 0 and it is also 0. Okay. So what can you do? So here the rank cannot be 3 because order of the matrix, because determinant of the matrix is 0. Now you will not be able to find a matrix, a submatrix of order 2 cross 2, which will give you non-zero determinant. There will be no matrix of order 2 cross 2. Suppose these two values are also 0. Then again, the rank will not be equal to 2. Okay, so you have only submatrix of order 1. Either it is, you take either 1 or 2. So determinant of this matrix of one element is 1, and determinant is here 2. So you have a submatrix of order 1 only, which is giving you non-zero determinant. So in that case, the rank of the matrix will be 1. This is notation for 1. This row A means rank of A. Are you getting this point? So the definition is that if there is at least one non-zero minor of order R and all the minors of order greater than R are 0. So if I have made here these 0, so you can see that there is only one minor, there is non-zero minor of order 1, and all the minors of order greater than 1 means of order 2 or order 3 are 0. Okay, minor 0 means determinants are 0. Okay, so you can see that here the rank is 1 if I have changed these two zeros. Otherwise, the rank was 2. Are you getting this by using the concept, by using this definition? Arnab, is it clear to you? Okay. One more example is there. Here in this question, the matrix is of order 3 cross 4. This is of 3 cross 4. But for minor or for determinant, you can see only for square matrix. So first you can find the square matrix of what? The higher order is 3, 3 cross 3. So I have taken this some matrix. So its determinant is non-zero. That is why the rank is 3. If it is 0, if the determinant is 0 here, then we will move for the sub-matrices of order less than 3. Okay, so then first we will check for order 2, then we will, if that is also 0, then we will move for order 1. Okay, so we are actually what we are doing, we are going in reverse direction from higher to lower order. You can also start from lower to higher. Then you will see that, okay, you have some matrix of order 1 giving non-zero. Okay, then matrix of order 2 is also giving non-zero. Then you will check for 3. But I think I like this method to go from higher to lower. Okay, so in reverse direction also you can move and you can find the rank. Okay, is it okay, Zorli? Vivek? Okay, good. So this was you got that how to find rank by using the definition. Now we will understand how to find the rank of a matrix by converting the matrix in echelon form. So before to find the rank of a matrix by echelon form, we must understand what is echelon form. How a given matrix looks like when it is in echelon form or not. Okay, how it looks like when it is in echelon form. So I have written some points here. So yes, so let's discuss these. So first point is the first non-zero element in a row should be unity, should be 1 if possible. It is not compulsory to have it 1, but if it is 1 then okay, otherwise it will work. So if we try to make the first element in a row with non-zero element in a row 1 if it is possible. Okay, and what are the benefits of making it 1? You will learn when you will study these about these echelon form. Okay, so it is not compulsory to be 1. Another point is that rows with all zero element must below of all non-zero rows. So you can see that here in first example, you can see that here the first condition is that the first non-zero element in a row must be 1 if possible. Okay, so it is 1 here in this row. But in second row, the first non-zero element is 2. In this second example, you see that the first, in B, in first non-zero element is 1 here. In second row, the first non-zero element is 2. In third row, the first non-zero element is 3. So it is not compulsory to have the first non-zero element equal to 1. If it is 1, then fine. If it is not 1, then okay. Okay, no problem. Then another point was the rows with all zero elements. If there is a row in a matrix having all zero rows, it must be below of all rows. Like this. You can see in the example in this C example. This row, this matrix has a row which has all zero entries 0, 0, 0. So it is lying at the bottom. Okay. So if there is row having all zero elements, then it must lie at the bottom. Okay, below of all non-zero rows. Okay, then the row will be in echelon form. And another condition is that the number of zeros preceding the first non-zero element in a row must be less than the number of zeros preceding the first non-zero element in the next or succeeding row. What does it mean actually? See, it is saying that when you move from up to down in a matrix, number of zeros before a non-zero number must increase. You can see that in example A, before 1 there is no 0, but when you move in the second row there is 1 0. In example B, you can see that there is 1 0 in second row and there are 2 zeros in third row. The number of 0 has increased. Okay, so this is fine. You can see in example C, you have 1 0 in second row before this one. Don't count this 0. You don't have to count the 0 after 1. We are talking about the 0 before non-zero number. So here it is 1. So before 0 there is 1 0. In the next row there are 3 zeros. So as you are moving from up to down, number of zeros are increasing. And which type of zeros? Before a non-zero number. Okay, number of zeros are increasing. See in example D, you have 1 0 here before a non-zero number. Here in another second row, you have 2 zeros. Okay, it is fine that number of zero has increased. But when you move to the third row, number of zeros is constant. It is not increasing. This means that it is not following all the points. So this matrix is not in echelon form. So for a matrix to be in echelon form, all these must be satisfied. If there is a row of all zeros, it will lie at the bottom. Okay, if there is. Okay, or the number of zeros before a non-zero number must increase. These may not be constant. Okay, so like in this example D, this condition is not satisfied, so this is not in echelon form. In example this E matrix, you can see that there is no zero in first row. In second row, there are 2 zeros before a non-zero number. In third row, there is 1 0 in a non-zero number. So this means here number of zeros are not increasing. So it is not in echelon form. Okay. Now in this F example, in this matrix, you can see that number of zeros are here 1 before a non-zero number. Here the number of zeros are 3 in third row before a non-zero number. The number of zeros have increased when you go from up to down. Okay. And there is no row having all zeros, so that's fine. So this matrix is in echelon form. So this A, B, C, and F, these are in echelon form. Matrices D and E are not in echelon form. Okay, so I have just tell you how a matrix looks when it is in echelon form. Sai Ram wants to ask something. You have raised your hand. You can write your query. Can you write your question in the chat box? Okay. Now you know which matrix is in echelon form, which matrix is not in echelon form. But if it is in echelon form, then it is fine. I'll tell you how to find its rank. But if it is not in echelon form, then what to do? Then you can convert the matrix in echelon form. But how? By applying elementary row operations. Actually, echelon form is also known as row echelon form because we will apply row operations. Okay. Column echelon form is different. So mostly we use this row operations. Okay. So we use row echelon form. So by applying elementary row operations, you can convert a matrix to a echelon form. So if you have converted a matrix in echelon form, then what will be rank? Rank will be the number of non-zero rows in a row echelon form. Number of non-zero rows in echelon form will give you rank. So in this matrix A, you can see that this is in echelon form. How many non-zero rows are there? There are two non-zero rows. So it has rank. This B matrix has rank 3. It is in echelon form. And the C matrix has rank 2. Why 2? It is in echelon form. But why 2? Because here you can see the definition, number of non-zero rows. So it has one row which has all zero elements. So don't count that. What are number of non-zero rows in this matrix C? Number of non-zero rows is 2. That is why the rank is 2. In matrix F, you can see that there are 3 non-zero rows. So this has rank 3. Samiram is saying matrix F is not having the pattern of increasing zeros, right? As we move from 1 to row 2 and then further to row 3. Why not increasing? You can see that in matrix F, you have 1 0 before this one. Don't count the zeros after non-zero number. I am talking about the zeros here before a non-zero number in a row. So in first row, there is no zero before a non-zero number. Okay. So 0, no zero. And in second row, there is 1 0 before a non-zero number. In third row, there are 3 zeros before a non-zero number. So number of zeros are increasing as you go from row 1 to row 3. Is it okay, Sairam? Are you getting my point? Okay. Don't worry, I will discuss about several matrices. I'll tell you how to reduce a given matrix, then you will be much comfortable with this concept of echelon form and the rank. So let's discuss. So here you have given a matrix. Now you have to convert this matrix in echelon form. Because when it will be converted in echelon form, then it is very easy to find the rank. Then you have to see only the non-zero rows. Okay. Non-zero rows means at least one element will be non-zero. Okay. Now the main thing is to convert this in echelon form. So how to do that? So you have given matrix 1 2 3 1 4 2 2 6 5. Okay. So what to do? In first row you have non-zero element 1. So that's fine. So what will we do? We know that for echelon form there will be zeros um, below the non-zero number in a row. You can see in all examples also. In first column, you can see that in every echelon form, you can see that you have one or a non-zero number and all other numbers are zero below that. Okay, so what will we do? We will apply row operations and we will make the first entry in R2 and R3 equal to 0. So what will you write? In R2, you have to apply the operation. So you will write R2 arrow R2 minus R1. R2 minus R1 or R2 plus minus 1 time R1. Okay. Then in R3, what you have to do? R3 minus 2R1. Or you can write it like R3 plus minus 2R1. Okay. So it will give you what? First row will be as it is 1, 2, 3. Right. Okay. So can you tell me what will be the entries in second row? What will be the entry in the second row when you will apply this operation of R2 minus R1? What will you get? Yes, 0, 2, minus 1. Good. What about this R3? What will you get when you will add minus 2 times of R1 in R3? So minus 2 into 1 is minus 2 and 2 is 0. Then minus 2 into 2, minus 4 plus 6, 2. Then minus 2 into 3, minus 6 and 5 minus 1. Yes, good. So you have 0, 2 and minus 1. Okay, so now you have 1 in first row and all zeros below this. Now we will move in the second row, because the rule is that the first non-zero entry in a row must be 1 if possible. So in first row we have make this 1. This was already 1. We have made zeros below it. Now we will enter in the second row. When you will enter in the second row, so you have non-zero entry as 2. Okay, so there are two things. Either you make it 1 or you don't make it 1. Okay, so I will advise you to make it 1 when the elements below it are not of its multiple or not equal. If the numbers below this element are lying in the same table, same or you can say multiple, then don't make it 1. Make the zeros the numbers below it. So without making this 2 as 1, we can make the element below it, this 2 in R3 as 0. So what I want to say, you can make this in R3, you can make this 2 0. So R3 minus R2 you can apply. So it will give you what? It will give you the first row as it is, second row 0, 2, minus 1, another is 0, 0. Okay, because the first non-zero number in a row to be 1 is not compulsory. That is why I have not made this 2 as 1. I have made 0 below this. Okay, but suppose if it is like 0, 2, minus 1 in second row. Okay, and suppose it was 0, say 3 and minus 1 like this, then this 2 and 3 are not multiple, not equal, or not in the same table. So in that case, what will you do? In that case, you will make this 2 as 1, then that 1 will help you to make this 3 as 0. Okay, because these are not multiple, not equal. Okay, so in this case, you will have to make this 2 as 1 and 3, and then you will make this 3 as 0. But here in this case, we have same number, this 2 2. So make we could made this 2 in third row as 0 very easily. Okay, so in this way you can do. So now you can see that this matrix is converted in row echelon form. Why row echelon form? You can see that number of zeros are going to increase. Okay, and the row having all zeros is lying at the bottom of the matrix. Okay, so now the question is, what is rank? If you have to find the rank, then what is rank for this matrix? Can you tell me what will be rank here? Yes, 2. Why 2? Let's Sainam is saying 5. Shiva, why 5? Let's say if we had 3 in third row, we would have made the 2 in row 2 as 1. Then we would do R3 minus 3R2. Yes, good. Is it like that? Yes, Ainam. Absolutely correct. Shivai, you are saying, dear, yes, number of non-zero rows, but you are writing 5 means you are counting number of non-zero elements, non-zero entries. So don't count number of non-zero entries. You have to count the rows. So you have this first row non-zero and this second row. Third row is the all of zero, na? So don't count this. So you have only 2 rows which have non-zero elements. That is why the rank is 2. Okay. You have to ignore, or you have to, you don't have to count the zero and the rows. having all zero numbers. Okay. So non-zero row means at least one element will be zero. At least one element will be non-zero there. Okay. Okay, Shiva. So, uh, one more matrix is there. So I'll discuss this also because then you will be much comfortable. I think this is different. Yes. So here you can see that you have one in the first row. So it's good. So you don't have to change this. So let's write one. Um, one, two, three, three, one, two, two, three, one. Now, can you tell me which operation is to be applied here first? Can you tell me how to proceed for having a row echelon form? R2 minus 3R1. Very good. R2 arrow. Because we are applying in R2 na, so we must write R2 arrow. R2 minus 3R1, and in R3 also. Okay, you can apply same time. Then R3 also, it will reduce your time. Okay, so R3 minus 2R1. So what does it mean actually? You have to multiply by minus 3 in R1 and add in R2. So what do you have in R2? 0 and minus 3 minus 6 and 1 is minus 5. Minus 9 plus 2 is minus 7. I always do addition by multiplying by minus that number. I always add. Okay. So in R3, what do you have? Minus 2 into 1. So it will give you 0. Minus 2 to 4, minus 4, and it is minus 1. Minus 6 plus 1, minus 5. Yes. Now, what to do? Now you have in first one in first row and zeros below this one. Now you have to move in the second row. So in second row, you must have here the number equal to 1 if possible. Okay, now you can see that this 5, minus 5 and minus 1. Now what can you do here? These are not multiple. Means multiple because minus you can directly this made 0, this minus 1 directly you can do that. These are multiple, not, but how will you do that? There are so many ways. Either you bring this minus 1 here, then make that an element 0, or you can directly, what can you do? There are so many possibilities. The easy thing is that you can interchange R2 with R3. Okay, because it is very easy when you have 1 or minus 1. So 1, 2, 3, 0, minus 1, minus 5, 0, minus 5, minus 7. Okay. Now it will be easy for you. Now you can make this minus 1 equal to 1 by multiplying by with minus 1. Okay. So if you multiply by minus 1, then you have here 1. Otherwise, without making it 1, you can do directly. So what can you do directly? In R3, you can subtract R3 um, minus 5 times R2. Are we allowed to interchange rows all the? Yes, this is elementary operation. Na? I discussed three operations: multiplication by a non-zero number, interchange of two rows, and the operation like this that we have done here. Addition of a multiple of row into the another row. Okay, so you can do that whenever it is required. So when you will apply this operation, R3 minus 5. Minus 5 means this will be R3 minus, no, not minus 5, it will be R3 minus R3, you can like write this. Okay. So R3 minus 5 R2. R3 plus minus 5 or R3 minus 5 directly. So what is will it give it to you? It will give you 1, 2, 3, 0, minus 1, minus 5. And when you will multiply by minus 5 in row 2 and add in that. So you have here 0 and minus 5 plus 25 and 25 minus 7 is 80. So you have this. Okay. So in this way you have matrix in row echelon form. Is it okay? What will be rank here now? Y2. What is answered by others? What will be rank? What will be rank, Arnab? Jorli? What pattern? Are you okay that this matrix in echelon form? This is echelon form or not? This matrix is echelon form or not? If it is not, then you should proceed. You must apply another operations. If it is not in echelon form according to you. If it is in echelon form, then what are number of zeros? Number of non-zero rows. What is the answer? Arnab is saying 3. Zorli, Shivai, Vivek, what are your answers? What is the rank of this matrix? And let me know that whether it is converted in echelon form or not. I missed that last row should have all zeros, right? No, no, not all zeros. You can see that the last row has 0, 0, 18, na? Last row has 0, 0, 18. It is echelon because number of zeros increasing top to bottom. Is that correct? Yes. Yes, Arnav. Yes, Shivai, correct. Here the rank is 3. Number of non-zero row is 3. Okay. When you will follow the pattern, what is the pattern? First, you have made the non-zero, you must have non-zero entry in a first row as 1. Okay, if it is not, if it is possible. So it make 1 and or make all other entries below this as 0. Then move in the second row. If possible, the first non-zero entry, make it 1 or minus 1. Okay. Then make all zero, all elements below this equal to 0 that we have done here in the last matrix. Okay. Then move in the third row. Okay. Because there is no another row, fourth row, so I have left here, or otherwise you can make this at 18 as 1. If you will multiply by 1 upon 18 and R3, suppose you multiply in R3 by 1 upon 18, then you will get here 1 in place of 18. Okay. So or otherwise you can left this matrix till this step because 1 is not necessary to be here in this row echelon form. I hope it is clear to all. Let's move to find the rank by normal form. Now you will see that in normal form, it is compulsory to have 1. The non-zero entry in a row, it must be equal to 1. It is compulsory. Okay. So see what is normal form. The make the first non-zero element in first row equal to 1 by applying elementary transformations. So it is compulsory to have 1. Okay. But other than that, what is compulsory? Obtain zeros in the remaining elements of first row and first column. Means if you have 1 in a matrix, then all elements below it must be 0 and all elements in it row must be 0. Okay, so this will be one, or this will be non-zero entry one in that row and that column. Okay, so in normal form it is required. Okay, so we proceed like this for every row. Okay, and what we have actually, you will have the form like this. Means you will have, suppose you have here 1 0 0 0 0 0 0 0 0 0 0 0. So what you will have, you will see that you have here 1 0 0 1. This is identity matrix, and all zero below it and in the right side. Okay, or you can have like this 1 0 0 1 0 0. You will have like this. Okay, or you will have this identity matrix, means IR of any order. Okay, so you will see that because there is only one non-zero entry, which is one, and all zeros are there below it in the row of that one. Okay, so you will find only the identity matrix there, and all other entries will be zero. And what will be rank? Order of the identity matrix will give you rank. So let's discuss how the matrix will look like when it will be reduced in normal form. So first you have to select the matrix in normal form. So we will learn how to reduce, okay? But here you have to select whether the given matrix is in a normal form or not. So see in the first A matrix. So you have here one in the first row, all zeros there in the row and column. In the next one, you have here 0 and 0, and here you have 1. So actually you can see that you have identity matrix of order 3. So it is in normal form. Okay, and what is the order of this identity matrix? 3. So you have 3. Okay, so rank is 3. Rank is 3. In example B, can you find identity matrix? Can you see identity matrix in this? In example B, in matrix B, can you see a matrix? Can you find an identity matrix in this matrix? Identity, or you can say submatrix. Can you have? No, you don't have. Suppose this one was, if it this one will be here and the 0 will be here, then you will have identity matrix. But at present you don't have identity matrix, so it is not in normal form. Okay, so yeah, when you will convert in normal form, what you can do, you can change columns, because here it is compulsory to have zeros in the columns of that one also. So you can apply here column operations also. I think I have written somewhere. Uh, Here it is not compulsory to apply only row operation. You can apply column operations also. Okay, so this matrix B is not in normal. Now, what about matrix C? Whether it is in normal form or not. Why? Is there identity matrix of any order? Is there identity matrix of any order? Can you tell me identity matrix of order 1? You know that identity matrix of order 2, 1 0 0 1. This is identity matrix of order 2. You know identity matrix of 0 3, of order 3. This is identity matrix of order 3. This is identity matrix of order 2. But what is identity matrix of 1? This. Only 1. This is identity matrix of order 1. Only 1. So you can find this now. You have identity matrix of order 1. This matrix has identity matrix of order 1. So this is in normal. Okay. See the matrix D. See the matrix D. Is it in normal form? Now you have here identity matrix, but it is not in this form. See here. It must be either at the top or in the left, or like this or like this. Not in middle. Okay. This matrix D is not in normal form, but it can be converted in normal form. Okay. It can be converted if you change some rows or columns. If you will interchange, if you apply some operations, then we can convert this in normal form, but at present it is not in normal form. What about matrix E? Is it in normal form? What about matrix E? Can you find any identity matrix in this matrix E of any order? There are two ones. This means you must have identity matrix of order 2. But is it there? No, you don't have to identify two different identity matrices. Only one identity matrix of some order. So if you interchange these two rows, suppose if you interchange R1, R2, then you will have normal form. Why? You will have identity matrix 1, 0, 0, 1. Then you have identity matrix of order 2. But at present, there is no identity matrix of any order. So this is not in normal form. See, you have to keep in mind the above forms that I have mentioned here. Keep these forms in mind. Okay. If you will keep these in mind, then you will not do any mistake. What about matrix F? What about the matrix F? Is it in normal form? Yes or no? Zorli, Vivek, Shivai, Arnab? No. Why? Why no? What about others? Is this matrix in normal form? Yes. Suppose this in second row, last one. Suppose this one is equals to 0. If it is 0, now it will be in normal form because it has identity matrix of order 3. But at present, it is 1, so that is why it is not in normal form. Okay. So if you have converted a matrix in normal form, okay, then number of non-zero rows will give you rank, or order of the identity matrix will give you the rank. So let's see this with the help of example. We will try to understand this. So you have given a matrix, this 1, 2, 3, 1, 4, 2, 2, 6, 5. Now to have this matrix in normal form, what we must have? We want here 1, so that is already 1 in first row, first entry. First non-zero entry is 1. Now we must have all zeros below it first. So we will apply the operation in R2, R2 minus R1, and in R3 it will be R3 minus 2R1. So it will give you what? What will you have now? You will subtract, you will apply this operation R2 minus R1. So this will be 0. 4 minus 2 is 2. 2 minus 3 is minus 1. Then in R3, R3 minus 2 R1 means multiply by minus 2 in R1 and add in R3. So minus 2 plus 2, 0. Minus 4 and plus 6 is 2. Minus 6 and 5 is minus 1. Now you have this. Okay. But because you are going to reduce in normal form, that is why you want these 2 and 3 in first row. These also must be equal to 0. So you will apply column operation. So what will you apply column operation? In column 2, you will, because you have 1 here in first column, so you will take help of this column 1. So you will write C2 minus 2C1 and C3. In C3, you will write C3 minus 3C1. Okay. So application of this operation will give you zeros in place of these, and there will be no change in other elements. So you will have 1, 0, 0, 0, 2, minus 1, 0, 2, minus. Is it okay? Is it okay to all till this step? Okay. Now what to do? What to do now? You must have one here. So what can you do for that one? What should I do? Can you tell me what to do for make this 2 as 1? Column 2 minus 2c1. Column 2 minus 2c1. How it gives 0 in row 1? Achha, you are asking about this. C2 minus 2c1, how it is giving 0? Um, See, when you have, actually, what do you have here? You have 2 here, okay, in C2, 2, and minus 2C1. So 2 times of 1 is 2, so 2 minus 2 is 0. Why are you writing 2 minus 4? From where you are getting 2 minus 4? I think you are looking for R2. I'm talking about column, not row. This is column 1, this is your C1, this is your C2. So C2 minus 2C1, you have to do perform this operation, no? Okay, you got it, it's good. Now, okay, so first I need to write the operation that I'm going to apply. To make this 2, there are so many things we can do. We can interchange column 2 and 3 and then make that minus 1 as 1, or otherwise I can divide by 2 in row 2. So simply what I can do, 1 by 2 into R2. So this will be 1, 0, 0, 0, 1 minus half. 0, 2 minus 1. Okay. Now you can have this. After making this as 1, you have to make the entry and make the elements below this one as 0. Okay. So what will you do in R3? Mm, okay, Vivek, take rest. In R3, you will apply R3 minus 2R2. So what do you have? 1, 0, 0, 0, 1 minus half, and then when you will subtract when you will apply this operation, so what do you have? 0, 0, 0. Okay, now you have to make, can we have elements in fractions in the matrix? Yes, we can have, but always try to avoid these fractions, means always try to apply the operations so that you don't have fractions. Okay, but here I know that this will also become 0, so that is why here is no problem. Okay, otherwise it is little difficult to have to deal with fractions. Now for making this minus half as 0, what we do? In C3 you will apply operation C3 C3 plus half of C2. Okay, so it will give you 1, 0, 0, 0, 1, 0, 0, 0, 0. Now this is converted to normal form. Okay, now for finding rank, you can check two things. Either one of these two things. One thing is that number of non-zero rows. So you have two non-zero rows, row 1 and row 2. So rank is 2. Or you can identify the order of the identity matrix. So you can see that order of the identity matrix is also 2. So that is why the rank is 2. A is the matrix. So row of A and rank of A is. Is it okay? Okay, great. Now you have learned about rank, and the purpose of learning about this rank was to solve a system of equations. Okay, so I'm going to discuss about that. So see, if you have a system like this, three equation in three unknowns, or you can have more equations in more number of unknowns. So no problem. This method will work that I'm going to discuss with you. So first thing is that if you have system like this, then you can write the coefficient matrix as we wrote in case of Cramer's rule. Okay, so this is coefficient matrix. It is denoted by A. The column matrix of unknowns. Unknowns are here x, y, z. So you have this matrix x. It is denoted by x, and these scalars, these constants on right hand side, these are denoted by matrix B. Okay, so first thing is that the system of linear equations in three unknowns is converted in terms of matrices, and it is written like Ax equal to B. Okay, now this B on the right hand side, it can have all values equal to 0. O means 0 matrix having all entries 0, or it can be non-zero. Non-zero means at least one element is non-zero. Okay, so if it is 0, Ax equal to 0 type, it is homogeneous, as I discussed in previous file when we were discussing about Cramer's rule. Okay, so this is same, and if it is not 0, then it is non-homogeneous, you know. So I'm first going to discuss about non-homogeneous system. Gaussian elimination method for a system of non-homogeneous linear equations. Non-homogeneous means at least one of the constant is non-zero on the right hand side in this column vector B or column matrix B. So how to find that? How to find the solution by using the concept of rank. See, you have system like this Ax equal to B, and we are dealing with when B is not a zero matrix. Okay, so what will we do? We will find rank of the matrix A and the augmented matrix. What is this augmented matrix AB? See here, you have given the system of four equations in three unknowns. Okay, so what is augmented matrix AB here? AB means, right, A means coefficient matrix. So in first row, what are coefficients? 1, 2, and minus 1. So I have written 1, 2, minus 1, and the right side constant is 3. So it is written here 3. Okay, so AB means you have to write the coefficients of variables, means you have to write matrix A, and then you have to make this partition, and then you have the column matrix of B, which is 3, 1, 2, minus 1. Okay, so you can write this augmented matrix very easily. So what to do with this augmented matrix? So you can see here, you have to find the rank of this matrix A and this augmented matrix AB. You have to find the rank of both. Okay, if they have equal rank, both have equal rank, then solution will exist, system will be consistent. If they have different rank are not equal, then solution will not exist and system will be inconsistent. Okay, then it is categorized whether will have unique solution or infinite. I'll discuss that. So first see here, first find the rank for this augmented matrix. So when you have written this augmented matrix, what will you do? You will convert, you will find the rank. And for rank, you have learned the methods. First, you have learned the method to find the rank by definition, means by finding minors. Another was to find using converting in row echelon form. And third one was by converting in normal form. So I will suggest you, whenever you are doing for Gaussian elimination, then you have to find the rank by using echelon form. Okay, so when you have to apply row operations to convert this in echelon form, because at present it is not in echelon form. Okay, so to convert this in echelon form, you must have one first in non-zero entry. It must be 1 if possible, so it is already 1, so no problem. Now you will make all other entries 0. So I have applied these operations. Okay. So to make this 3 as 0, I have written R2 minus 3 R1. Then to make this 2 as 0, so it is R3 minus 2 R1. and in R4, R4 minus R1 is applied. These operations are applied and these are 0. Now you can see that when you will move in the second row, you have here minus 7 and you want here 1. So what I have done, I have applied this operation R3 minus R2. So when you will apply R3 minus R2, so it will give you 1 here, but it is in R3. Okay, so now interchanging this R2 and R3, you will get 1 here. So why I am getting 1 here? Because you can see that these elements minus 7, minus 6, minus 3, these are not multiple of each other, or these are not belonging to a table of some number. Okay, so in that case, when you don't have numbers multiple, so in that case it is very important to have 1, because this one will help you to find, to make all entries below that one equal to 0. So I have here 1 and here you have minus 7, minus 3. So now we have here 1. So it will help to make this minus 7 and minus 3 0 by applying this operation in R3. If you apply the operation R3 plus 7 R2, and in R4 if you apply R4 plus 3 R2, then it is very easy to have zeros here. So you have zeros. Okay, so you have to apply these operations very carefully. Okay. Now still it is not converted in echelon form. So when we will move row on row 3, so you have here 5 and 5 and 2 are also not in the same table, not multiple. So you will make this 5 as 1. So you can see that in this row 5 and 20 are there. Okay. So if you will divide by 5 in this row, it will be free from fractions, and you will have also 1 here in place of 5. So I have divided by 5, means 1 by 5 is to be multiplied in R3. So you have here 1. Now after having 1, you can make this to a easily 0, R4 minus 2 R3. So applying this operation, this is 0 now. Now this is converted in echelon form. Okay. So the first step was to find the rank of augmented matrix and the matrix A. This whole matrix of order 4 cross 4, it is augmented matrix. So what is the rank of this matrix? The rank is 3. Why? So when you ignore this row, because the last row has all zeros, so you will ignore this. So you have 3 non-zero rows. So number of non-zero rows is 3. That is why the rank of augmented matrix is 3. You have also find the rank of A. So for A, you don't have to proceed further. You will find rank of A from this the same matrix. How? When you will hide this last column, because it is the column of B, column matrix. Okay, so hide this and find the rank for this remaining matrix, which was from A of order 4 cross 3. So what is the rank of this matrix of order 4 cross 3 after hiding this matrix of B? So this rank is again here 3, because it has this 0 rows of all zeros. So it has rank 3 because it has 3 non-zero rows. Okay, so that is why rank of A is 3. Now both have equal ranks. Okay, so that is why solution exists. System is consistent. Okay, are you getting this? Are you getting this? Okay. So according to this, you can see that the first step was find rank of A and augmented matrix. So we have both. This is 3 and this is also 3. That example. So if these are equal, solution exists. Okay. So means solution exists in that case. System is consistent. That's fine. Then what to do? Now, if these ranks are same and these are equals to n means number of unknowns. If you have equal ranks and these are equals to number of unknowns, so then you have unique solution. If it is less than n, then infinite number of solution. Okay, so if it is less than n, then infinite number of solution. So you can see here ranks are same which is equal to 3, and it is equals to n number of unknowns. Unknowns, how many unknowns are there in the system? You can see from this question, there are 3 unknowns x, y, z. So your n is 3. So your n is 3. So rank are same and equal to the number of unknowns. This means solution is unique. You have unique solution. So this means there will be unique value of x, y, and z that will satisfy the given system of equation. And the now question is, what is that values of x, y, z? What is that solution? What is that unique solution? Okay, can you tell me how to find that? Is it clear to all? And tell me how to find that unique solution. What do you think? What to do to find that unique solution? It's okay, Shivai. Can you tell me? My question is, I'm saying both matrix A and the augmented matrix have the same rank, and this rank is equals to n, means number of unknowns. So this means that the system has unique solution. So my question is, how to find that unique solution? Can you tell me about this? How will you find the value of x, y, and z? Will you solve those 3 equations given at the starting of this question, or will you do another thing? What will be the method how to find value of x, y, and z? Elimination or row echelon form? You have already converted in row echelon form, na? So how to now find that solution? See, you will use back substitution. Number of non-zero rows have already given, and that has given you to the rank. Okay, number of non-zero rows have given you the rank. Now I am asking about the value of x, y, z. So see here, from this system. Oh, see from this system, from first three equations, first 3 rows. See this one, and here it is 4. So this one is for, well, this third column was for z. So you have what? Z equal to 4. 1 into z is 4, means z is 4. Okay, now move in the second row. Second row is giving you 1y plus 0z equal to 4, or you can say directly y equal to 4. Okay, now move in the first row. First row is giving you x plus 2y minus z equal to 3. Putting values of y and z in this equation, you will have value of x. So x plus 2 into 4 is 8, minus z is 4 equal to 3. So x is equals to 3 minus 4 equal to minus 1. You have values x equal to minus 1, y equal to 4, and z equal to 4. You can check this solution whether it is correct or not. So you can substitute these values of x, y, z in the given system of equation. Okay, if all these 3 are satisfied, then it's okay, and this means the solution is correct. So is it okay to you that how to find unique solution? Okay, okay, Sai Ram. So is this the Gaussian technique? Yes, Gaussian elimination method to solve the system of equation. So I have discussed one question when you have unique solution. So in unique solution, you must have the rank of matrix and the augmented matrix must be equal. Okay, so you must have equal ranks of both, and that those ranks must be equal to number of unknowns. If it is so, okay, then we have unique solution. If it is not equal to n, if it is not equal to number of unknowns, then you don't have unique solution. Okay, so I'm going to discuss another question also. See, in this case, First, you have to write augmented matrix like previous one. Okay. Now it is converted in echelon form. How it is converted? First non-zero entry in first row is made 1 by interchanging R1 and R2. By applying this operation, you have this 1 here. Now this 4 and 15. These are made zeros by applying these operations. Then if we move in row 2, you will see that here -6 and here you are -18. So -6, -18, these are multiple. So without making this -6 as 1, you can directly make this -18 as 0. So I have done directly. Okay. Or you can also divide in this R2 by -6. It will give you 1 because -6, 18, 12, these are multiple of 6 or -6. So you can get 1 also by dividing. But I have done directly. So now you can see that if you see this whole matrix, if you see this whole matrix of order 3 cross 4, so you have two rows which are non-zero and one row is of 0. So augmented matrix has rank 2. Okay. Now if you hide this last column of B, you see only on A. So matrix A has also rank 2 because it has two non-zero rows. So rank of A is 2. So rank of A is 2, rank of augmented matrix is 2, both are same. This means in solution, the system is consistent, system has solution exists. Augmented matrix was this. See here. Shivai, see here. This was augmented matrix. Means what you have to write? You have to write coefficients 4 minus 2, 6. 4 minus 2, 6. And the right side coefficient is 8. So this is 8 here. Okay. And this partition shows that this last column is for B. So we write like this. So in augmented matrix, the column matrix B was also included. And whenever we talk about A, means only A, coefficient matrix. Okay. By taking the coefficients of the variables. Okay. So both have same rank. So system is consistent, solution exists. But which type of solution? Unique or infinite? So you can see on this here. You can see that I have already mentioned if both are same and equal to n, then unique solution. If both are same, both ranks are same, but less than n, then system has infinite number of solution. Okay, so these ranks will be, if these are equal, so these will be either less than n or equal to n. So equal to n will give you unique solution, and less than n will give you infinite number of solutions. So this means that in this case we have here um, rank is 2, both have equal rank and it is equal to 2, but n is 3. Number of unknowns, number of variables is 3. So it is less than 3. So if it is less than 3, system has infinitely many solutions. Infinitely many solutions. Okay. So in case of unique solution, I told you how to find that unique solution. You have to move from third row to first row. So third row gives you value of z, second row gives you value of y, and first give you value of x. So in the first question, you did like this. But how to find solution here in this case? Can you tell me how to find infinite solution in this case? See, again you will move here from uh, last non-zero row to first non-zero row. But you can see that if you write equations, you will see here you have two rows, three unknowns. Means you have lack of one equation. If there are three variables, there must be three equations. But there is, you don't have one, you have one equation is less. Okay. You are lacking with one equation. So this means you must assume one variable. So I suppose z equal to say k. Okay. So this second row will give me, it is giving -6y plus 18 z equal to 12, and you have assumed z equal to k. So what will be y now? Minus 6y equal to 12 minus 18k. So y will be minus 1 upon 6, 12 minus 18k. Or if you will divide by 6, so you have minus 2 minus minus plus 6 3 is 18. So you have y equal to minus 2 plus 3k. What is k? Any arbitrary constant, any number. Okay, k belongs to R. Now, if we write equation from the first row of this echelon reduced matrix, which is in echelon form, so you have x plus y minus 3z equal to minus 1. Now you have values of y and z, so you can find value of x. So x will be what? X plus y is minus 2 plus 3k, then minus 3k equal to minus 1. So minus 3k and plus 3k cancel out. You have x equal to 1. So in this way, you have x equal to x equal to 1, y equal to 3k minus 2, z equal to k. So you have solution in terms of. Now you can think that how you have infinite solution, because you are looking and you have only this value x, y, and z. See, this value is in terms of k. Now k can have infinitely many values. Okay. Yes, Arnav. Now the solution will be in terms of k or k1 or k2, any variable or t. You can take anything. Now this k can have infinitely many values. That is why you have infinitely many solutions. How? See, suppose I take k equal to 1. So your solution will be x equal to 1, y equal to 1, z equal to 1. If I take k equal to 2, so x will be 1, y will be 6 minus 4, 6 minus 2, which is 4, and z will be equal to 2. Okay. So you have value x, y, z. You have this value of x, y, z. So similarly, you can have infinitely many values. Okay. So infinitely many solutions means you will have these values in terms of k or k1 or any arbitrary number. Okay. So in this way, you have infinitely many solutions. But when you have unique solution, these will be only numbers, unique values. Okay, so you must know what is the difference when we have unique solution and when we have infinite solution. In case of infinite solution, the rank of augmented matrix and the given matrix is same, but it is less than the number of unknowns. But in case of unique solution, these ranks are same and it is equals to the number of unknowns. So is this case clear to all? Okay. Let's discuss one more question on this. So you are here, you have three equations in three unknowns. So first I have written this augmented matrix. Then we have already one here in the first row, first entry. Then these 3 and 2 are made zeros by applying the operations. Okay. Now you can see that when we will move here in the second row, you have here minus 2 and 2. So it is very easy to make this 2 as 0 without making this minus 2 as 1. So I have made this 2 in the third row 0 directly by adding R3 and R2. So you have this. Okay. Now this is reduced in echelon form. If you see this whole matrix of order 3 cross 4, you have this in echelon form. Now, what is the rank of the whole matrix? How many number of non-zero rows are there in this matrix of order 3 cross 4? How many number of non-zero rows are there? How many rows are there which are non-zero? 3. So that is why the rank of the augmented matrix is 3. Good. Okay, so rank of augmented matrix is 3. But suppose I want to ask for matrix A. So for that a matrix A, you have to remove the last column. So now remove the last column of matrix B and see this matrix of order 3 cross 3. Now, what is the rank of matrix A here? If you hide or remove the last column, then what is the rank of the matrix here? This is 2 because it has one row of zeros, all having 0 elements. So the rank of matrix A is 2. So in this case, rank of A and rank of augmented matrix are not equal. So for a solution to be there in a system, these ranks must be equal. If these are not equal, then system solution does not exist. System is not consistent. It is inconsistent. I have already written here in the steps here. Yes, see here in the right hand side. When these ranks are not equal, solution does not exist. System is inconsistent. No solution. Okay, or there is no need to write. I think so. Since there is no solution, solution does not exist. System is inconsistent. Okay, it is enough. So if you have equality of these ranks, then there is possibility of solution either infinite or unique. If these ranks are not equal, then solution does not exist. Okay, so only 3 possibilities are there for solution. So I have discussed one question for each case. So we have discussed so far in Gaussian elimination the system of equations and which was non-homogeneous. Okay, now I have to discuss for the system of homogeneous linear equations. Homogeneous means you have all zeros in the right hand side in the constants. All are zeros. So system is homogeneous. Now how to find the solution for this? I am going to discuss this. So is there any question to anyone up to what we have did? So what we have done, is there any question regarding this Gauss elimination? Okay. So let me complete this now homogeneous linear system. So in homogeneous, uh, you have all zeros in right hand side. Okay. Now see, this homogeneous system always has a solution. Always. Why? What will be that solution? See, if I have written here 4 equations in 3 unknowns. So can you tell me directly the value of x, y, z that will satisfy all these equations? Is there any value of x, y, z that will satisfy all? See, you have zeros on right hand side in each equation. So can you tell me the value of x, y, z that will satisfy every equation? Now it is very easy. So what is that? -1? Why -1? I'm asking for the value of x, y, z. Yes, Shiva, good. If you put x equal to 0, y equal to 0, and z equal to 0, then all these equations will satisfy. Okay. So all these will satisfy. This means this is trivial solution. It will always exist. Now the possibility is that whether there is another solution other than this trivial solution. Okay. If no, if it is only solution, this means this is a unique solution 0, 0, 0 that will satisfy. Okay. If yes, yes, then there will be infinitely many solutions. So see here, first thing is that it has always a solution. Okay. Now it is clear to you that why always? Because 0, 0, 0 will always satisfy such a system. Now another thing is that uh, to identify whether this solution is unique, this is only the solution 0, 0, 0, or there is another solution which exists and satisfy the system. So for that we find the rank. We find the rank. If rank of the matrix is equals to the number of unknowns, then the system has unique solution. And that unique solution will be trivial solution. Trivial solution means 0, 0, 0, 0. Values will be 0, 0, 0. But if the rank is less than n, less than number of unknowns, then the system will have infinite number of solutions in terms of k, t, or other variable. Okay. So infinite solution means non-trivial solutions. Okay. And one more thing is that when system has unique solution and this the determinant of the coefficient matrix will be non-zero in this case and zero in this case when it has non-trivial solution. Okay. So let's discuss a question based on it. So in this question, you have given four equation and three unknowns. So you have to take only matrix A because the column matrix is zero, so there is no need to take augmented matrix. You have to consider only matrix A, and you have to convert this in echelon form. So now I think you are comfortable with echelon form. So I have converted this in echelon form like this. So what is the rank here? Here there are two rows which have zero elements. So rank will be only 2 because number of non-zero rows are okay. But how many unknowns are there? Unknowns are there 3, n is 3. So this means system has infinite number of solutions. Okay. So how will you find infinite number of solution? Using the same method as I discussed in case of Gaussian elimination for non-homogeneous. This is also Gaussian elimination. We are doing the same Gaussian elimination, but now only the different thing is that we are doing for homogeneous system. So in a similar way as we did uh, in the non-homogeneous system, you will assume because you have two equations now, these two equations from this last matrix. So I have assumed y equal to k. So this is giving you z equal to minus 7. Or you can assume z equal to k. This will give you y equal to in terms of k. Because but for avoid fraction, I have taken like this. I have assumed yk, then z will be minus 7k. Okay, if you take z equal to k, then it will give you y equal to minus 1 upon 7k. Okay, so both are correct, no problem. So for this y and z, I have uh, got the value of x from equation 1. So this equation x plus 3y plus 2z equal to 0 gives value of x as 11k. Okay, so in this way, you have solution in terms of k. This means you have infinitely many solutions. So this was about for Gaussian elimination for both homogeneous and non-homogeneous system. So is it okay to all? Any query to anyone? Okay. What about you, Sairam? Okay. Any query? I am listening but unable to follow completely. Why? If you have any query, any confusion, so you can ask. Otherwise, you can also go through the recordings after the class. Okay, and you must solve all these questions by yourself. Okay, so then you will be much comfortable with this echelon form, with the concept of rank, and with this Gaussian elimination method because it is very, very important. Okay, so you must try to solve all these questions by yourself. So that will help you and you will be much confident with these concepts. Okay, so I think we must have a break. Parth, are you there? So let's stop here and we will have break for 15 minutes. So we will resume 3:20, 30. We will resume around 3:35. Okay. Okay. So let's start the discussion on vector space. How many of you know about this vector space or the concept of vectors? How many of you know? Sairam, Shivai, Arnab, do you know what is vector space or what do you mean by vectors? No idea. Okay. Do you know about vectors? Yes, from high school. See, just a minute if I add another page here. You might be knowing about vectors like this. Suppose you have a point here, O, you have a point P. If I join this O to P, so OP is a segment, line segment. If I am putting here direction, so this means O to P. If I write like this, so this means there is a direction from O to P. Okay, and magnitude is also associated with this. How? Because length of this length of this vector. So length of this vector, suppose this is vector V. I denote it this as V. Okay, so we can also find its length. If I can find its length, it has direction. So I think you have studied about vector quantity. Vector quantity means the quantity having both direction and magnitude, like velocity. Okay, so it has both magnitude and direction. So the quantities having magnitude and direction are called vector quantities. What about vectors? So here vector means you are going in some particular direction from O to P. Okay. So whenever you deal with vectors, so I think if you have studied something about vectors, so you might be knowing about a vector like, suppose you have a vector 2i plus 3j. Do you know like this? Where I and j are, I cap and j cap are unit vectors along I axis, along x axis and y axis. If you have vectors like this, suppose this is vector v1, another one is vector t2, v2. Suppose 3 I cap minus 4 j cap. Then you can add these vectors. Or if you have vectors like this vector, one vector is this, then you can find the addition and subtraction of these vectors also. If I have this vector v1 and v2, so can I and j, I can add these vectors. So it will be 5 I cap minus j cap. I cap and j cap are unit vectors along x-axis and y. I cap is unit vector along x-axis, j cap is a unit vector along y-axis. Okay, so we can add two vectors. We can add two vectors, we can subtract two vectors, we can have product of two vectors, and product is also two types, a scalar product and dot product. Sorry, dot product and vector cross product. Two types of products are there. So do you know about that, Arnab? Because I have not mentioned in this file those basic terms. Suppose you have a suppose you have a point here 2 comma 3. So vector associated with this is this. In physics, actually we write in terms of 2i plus 3j, or in mathematics we write like this, vector v equal to 2 comma 3. And instead there is also no need to write this arrow. Okay, so we write like this. So basically if you have a vector say 2 comma 3, okay, you have a point 2 comma 3. So if you write in terms of j and I and j, so it is written as 2i plus 3j, like this. Okay, so what is this actually? It is that you have this from this O, you are going, voice is cracking. Hmm, there may be some network issue. So what? Okay, Shiva. So let's see, if you want to know about this, let's see here. Just I'm doing again. I'm telling you something about that you do in physics or in other places, in other subjects. If you have vector say v1, 2i plus 3j. If you have suppose another vector v2, say 3i plus 4j. So what do? you add these vectors. You can add these vectors, you can subtract these vectors, okay, or you can multiply these vectors. So how will you add? You add component wise, you add these multiples of I, so you have 5I plus 7j. If you subtract from v1, if you find v1 minus v2, so you have minus I and minus j. You have these vectors. And what does this represent geometrically? That can also be learned very easily. So I'm not going to discuss that here much. And if you want to find the dot product of these two vectors, so dot product means 2I plus 3j dot 3I plus 4j. You do like this. Do you remember this if you know something? So when you multiply, so you have I dot I means I square, which is, or you can say don't I square. I dot I is 1, j dot j cap is 1, k dot k cap is 1. And if you have different means if I am taking in two dimensions, so there is no need to write this k. And I dot j is 0, or j dot I is 0. So here you will have here only, this will be multiplied with this 2I into 3I, it will give you 6, and 3j into 4j gives 12. So in this way, this gives you a scalar quantity. So whenever you have dot product of two factors, it gives you scalar quantity. Actually, I will discuss it later when I will discuss about inner product space. So what I want to say you, we have to learn about vector space. So whenever we study vectors, there is a vector addition and scalar multiplication. What is scalar multiplication? If I have drawn this vector, okay, if I want twice it's twice, so twice means it will be twice means the vector will be um, two times of this. So if you have a vector v equal to, if I am writing in terms of I and j, I cap j cap, if this is v, then what is 2v? 2v is two times of this means 4I cap plus 3j cap. So you will have some point here, 4I cap plus 6j cap you have here. So twice means its length will be twice, okay, or if vector it will point to some another point, okay, so with that will be at the twice distance from the previous point. So in vectors you have the concept of vector addition and scalar multiplication. Why scalar? Because you are multiplying by a number, and what is the number? Number is a real number, okay. So in vectors you can add two vectors, okay. Whenever you have this vector, suppose you go from this to this point, and then you go from this to this point. Suppose this is O, this is A, this is B. You go from O to A and A to B. Then what is this vector from O to B? This is actually the sum of these two. This vector OB is what? Actually OA plus AB. Okay. So you can so what do you have? You can add two vectors, or you can multiply a number in a vector. So when you multiply 2, so you have another vector, okay, and length will be twice. If you multiply by 3, you have another vector, and length of the vector will be thrice, okay. So whenever you are multiplying by a number, scalar, okay. So you have these two operations in vectors when you study vectors in your plane or in space, okay. But there are so many mathematical spaces where the concept of vectors was generalized, okay, because this two-dimensional plane, three-dimensional plane, these are particular examples. I will discuss that how these are vector spaces, but there are some other also mathematical spaces, okay, where you can generalize this concept, means where you can have addition of vectors and scalar multiplication of vectors. Scalar multiplication means you will multiply a vector by a scalar. What will be the scalar? You will see that here. What will be scalar? I will tell you, okay. So in the case of vector, when you study in plane or in space, you take scalar from real numbers, set of real numbers. Okay. So vector space is actually what? Vector space, as the name suggests, space of vectors. Okay. This means it has set of vectors. It has non-empty set V of vectors. Why non-empty? If it will be empty, so how it will be space? How it will it create a space? So it is non-empty set of vectors. Field f of scalars. As I told you, whenever we have vector v, if we are multiplying by 2, so 2 is a scalar. है ना? We are multiplying by 2, we are twicing that. Okay, so 2 is a number. So the number or the scalar that is multiplied in that vector, that is taken from a field. Actually, field is a system that I'm not going to discuss in depth, because those who knows about the group theory or field theory, they will be knowing about what is field. So I'm not going to discuss that field, but you can think that always the scalars, always the number that has to be multiplied in the vector are taken from that field. Okay. So here I will only discuss about the field. Field means I will take the constants or the scalars from real numbers mostly. In all the questions, I'll take from reals. Okay. So you can think that it as a set of reals for real fields. Now, vector space that I'm considering it is system. This set of non-empty set of vectors, this field of scalars, and there are two operations: vector addition and scalar multiplication. As I discussed with you, if you have vectors, then you can add them, and you can do scalar multiplication. So here are also two operations there: scalar multiplication and vector addition. But these two satisfy some properties, some axioms. So what are these properties for these operations? For vector addition here plus is the addition sign. Okay. So what properties will it satisfy? The first property is closure law. Closure law means if you have two elements of vector space V, if I am denoting this by V, if I take two elements, then the addition of these two will be a vector. Alpha plus beta will also belongs to V. Then another property is associative law. Alpha plus beta plus gamma is same as alpha plus beta plus gamma. Here, the addition is done between beta and gamma, then alpha is added. Or if I first add alpha and beta, then I add gamma, then both are same. Okay, as you can also do in case of your real numbers. If you have three numbers, if you add first two and then third one, or if you add last two and then add the first one, you will have same value. Okay, so this associative law is also satisfied there. Next property is existence of identity. Existence of identity means if there exists a unique vector 0, such that if you add that 0 vector in your alpha is any vector, then you get the same vector. Okay. So you know if in case of real numbers, if you have 2, and then you add 0. So you have 2 plus 0 equal to 2. Or you add 0 plus 2, then again you have 2. So 0 is the identity element. Okay. If you have points in R square, if you have suppose 2 comma 3 and you add 0 comma 0, okay, then you will have 2 comma 3 again. If I write this 2 comma 3 vector in terms of ij as you write in physics, then this just things are similar. Okay. But ij unit vectors are used in your physics and some other fields. But when we do mathematical study, we write always in ordered in these tuples in pairs. In R square, you have pair like this. In R cube, you have tuples, you have three numbers. Okay. So in mathematics, we write like this. Now, existence of inverse. There exists a if there exists a unique vector minus alpha denoted by minus alpha, this is not the minus that you know. Minus alpha means inverse of that alpha, such that if you add that minus alpha in your vector alpha, it gives you 0. For example, if you have 2 in your real number, then which number, suppose this is number x, so which number you will add in 2 that will give you 0 number, so that you can say that x is minus 2. Yes, so you can say that x is minus 2. So minus 2 is additive inverse of this 2, because when you are adding this 2 with this minus 2, it is giving you 0. Okay. Similarly, suppose you have ordered pair 2 comma 3. So which number you will add here? Suppose it is xy. So which pair x comma y will you add, so that you will have 0 comma 0 means 0 0 vector. So which number you will add? What will you take, x and y? So you will take x equal to minus 2 and y equal to minus 3. So that when you will add minus 2 comma minus 3, it will give you 0 0. Okay, so if there exists such element, so that for every alpha, if there exists another element minus alpha, so that the addition gives you identity element, 0 element, this means existence of inverse is there. Commutative law means if you add two elements alpha and beta, or if you change their order, both must have same value. Okay, if it is so, if it holds, then you say that the vector addition is commutative. Then in case of scalar multiplication, there are 5 axioms to be satisfied. The first one is C alpha belongs to V. If C is a scalar, alpha is a vector. C alpha is also belongs to V, means C alpha is also a vector. So say you have a vector 2 comma 3. 2 comma 3 means you have this point 2 comma 3. So this is your vector 2 comma 3. I'm not writing now in terms of I and j. You have this 2 comma 3. Okay. Now suppose I multiply in this by 4. So what does it give? It will give 4 2 is 8, 4 3 is 12, 8 comma 12. Okay, like this. So it is again a vector. It is again a vector in the plane. Okay. So this means it is following this rule, this property. So if C time of a vector is again a vector, then we say that this property holds. Now, if I multiply by 1 identity element, if I multiply by 1, then I have the same vector, then this condition holds. Okay, so 1 is actually multiplicative identity. So we only multiply by 1. 1 is multiplicative identity element. In different examples, I'll tell you what is 1. Now, what is 8's property? C1 into C2 alpha. If I multiply with C1 and C2, two scalars, then operate on alpha, multiply with alpha, or otherwise, if I multiply by C2 in alpha, then again C1. So these holds. If this equality holds, then this is satisfied. Ninth one is C times alpha plus beta is C alpha plus C beta. Okay, if C is multiplied, means if you add two vectors and multiply by C, or if you multiply by C in both alpha and beta and then you add, so both are same. So if it is satisfied, then fine. This is we have this property. 10th one is if we add two scalars. Now we have addition in two scalars. If we add them, then multiply by a vector, or if we distribute, so these must be equal. So there are 5 properties for vector addition, 5 for scalar multiplication. If these 10 conditions, 10 properties are valid, are satisfied, then we say that V is a vector space. Okay, let's discuss with the help of example. I have taken the first example as R square that I was discussing in the plane. Okay, not in terms of, now I will not take in terms of I cap, J cap. We will take in terms of ordered pairs. In mathematics, we take like this. Okay, so what are the elements of R square? Yes, full screen is there now. Arnab, what are the elements of R square? You know, This, if this is your plane R square, so you have elements like this, A comma B type, all pairs, ordered pairs. Okay. So if I want to check that whether R square is a vector space or not, we must have check, we must have checked all these. Okay. So we have to check if I'm talking about first this plus vector addition. So I must have this alpha and beta. So I have taken elements alpha as A comma B, beta as C comma D, gamma as E comma I. I have taken three. Is it okay? Is it visible? I have taken these three. Okay. Now, according to the first property is closure law. First one is closure law. So, closure law say, according to closure law, alpha plus beta belongs to V. Alpha plus beta. If alpha and beta in vector space, then alpha plus beta must also be in vector space. Gamma symbol is like Y. Yes, this gamma. This is, yes, not Y, but it is actually, it must be like this. So alpha plus beta, if alpha is A comma B, beta is C comma D, then addition of these two is what? A plus C. You add component wise. Why component wise? Because operation is given. See in the question, we have to prove R square is a vector space over R. Over R means constant will be real numbers. Scalars will be real numbers under addition and scalar multiplication. So addition means if you will add two ordered pair, so you have to add component wise, means first component of this, second of this. So x1 and plus x2. So x1 plus x2. Then second component is to be added. So y1 plus y2 second component here. Okay. So you have to follow this rule for addition. For multiplication, scalar multiplication, you have to multiply by alpha in x1 comma y1. So alpha into x1 first one, then alpha into y1. Okay, okay. So you will follow this. So for alpha plus beta, you have to this add alpha is a comma b, beta is c comma d. So addition will be a plus c comma b plus d. Component wise you have added. So you have added according to the operation which is mentioned in this question. Then you will see you have this ordered pair. So it is clear that this ordered pair is belongs to R2. Okay, so this closure law holds. Now second law is associative law. So according to associative law, we have to show that alpha plus beta plus gamma is equal to, means these two are equal. So what I have done, alpha is written, value of beta is written, gamma is written. First beta and gamma are added. So you have this value C plus E comma D plus F. Now it is added with this A comma B. So you have this added component wise. So A plus C plus E is this. A plus C E. Similarly, another value is B plus D plus F. Okay. Now if we add first alpha plus beta and then add gamma, then again you have this. So we can say that this equality holds and associative law is satisfied here. Okay. Third one is existence of identity. So alpha plus 0 must be equal to alpha. So I have taken alpha as A comma B, already mentioned. Now what is 0? What element should be added in A, this A comma B, so that we get again, we get A comma B again. So it must be 0 comma 0. If I add 0 comma 0, then I have alpha, A comma B, this is alpha. So alpha plus 0 is alpha. This means existence of identity is there. This 0 0 element is 0 0 element is the 0 vector or identity vector, or identity vector or identity element. Okay. Now, what about inverse? If alpha is A comma B, which element is to be added so that it gives 0 0? So it is what? Minus A minus B. Because when you add minus A minus B, you have A minus A, B minus B, which is 0 comma 0. So this minus A minus B is the inverse. Okay. Now commutative law. If you add alpha plus beta, so you have this a plus c comma b plus d. And you add if beta and alpha, beta plus alpha, then again you have a plus c comma b plus d. So in this way you have alpha plus beta and beta plus alpha. So commutative law holds. So in this way you can see that all the properties, all the axioms for vector addition are satisfied. Now we have to check for scalar multiplication. Is it clear to all? Is it clear so far that I have discussed about this vector space? Or you have any confusion, any kind of query? So please let me know so that if I know that if you have clear everything, then I'll move. Because I have to discuss several questions. I'll also discuss some questions which are not vector space. So not a vector space means if any one of the property is not satisfied, then not a vector space. If all these 10 holds, then vector space. So for having a vector space, we have to check all 10. Okay, for not having a vector space, if we show that anyone is not satisfied, then it is not a vector space. Okay. And are you able to connect this with the usual vectors that you study? So I told you that whenever you study about vectors, so there is a concept of vector addition, scalar multiplication. Okay, not talking about the product right now. So if you have the concept of vector addition and scalar multiplication there, so that is generalized here. Okay, and we can study that we have now concept of vector spaces after generalization, and for that for any set no set of vectors with operations vector addition and scalar multiplication and having some field of scalars, we must have the satisfaction of these 10 properties. These are hold. If these hold, then we say that that mathematical space, that mathematical system is a vector space. Okay, so first we are doing for R squares. Now let's check another 5 conditions for scalar multiplication. So under scalar multiplication, what was the first axiom? This C alpha belongs to B. If alpha is a vector, then C alpha must also be a vector. So I've already taken C, I think in beta. Beta was C comma D, na? That is why I have taken here C dash. Okay, not necessary to take C. I have taken C dash. So C dash alpha is what? C dash alpha is A comma B. So when you will multiply, so it is C dash A comma C dash B. Why it is multiplied like this? Because it was mentioned in your question. What was mentioned? You can see that in the question, it is mentioned that alpha into x1 y1 is alpha x1 comma alpha y1, means alpha is to be multiplied with each component. Okay, so that is why I have multiplied this C dash with this A comma B. So C dash into A and C dash into B. Next is 1 alpha. 1 alpha must be equal to alpha. So 1 alpha, now multiplying by 1 into A comma B. So you have A comma. So it also holds here. And next one is C1, C2 alpha. So you have alpha A comma B. C1, C2 is a scalar. Okay. When you multiply by C1, C2 in A and B, so you have this. But if you multiply by C2 first and then C1, so multiply by C2 in A comma B means C2A comma C2B, then multiply with C1, so you have this. Okay, so you can see that both of these are equal. So this means this property also holds. Ninth one is C1 alpha plus beta. So if you add alpha and beta, then multiply with C1. So alpha beta are added and multiply with C1. So you have this one. Now if you multiply by C1 in alpha and multiply by C1 in beta, like this. So this is C1A comma C1B, then C1C, comma C1D, and then you add. So you have this. So both are same. So this also holds here. Then last property is all to check. So C1 plus C2 into alpha is what? C1 plus C2 A comma B. Okay. C1 plus C2 is multiplied in A. So you have this term. Then C1 plus C2 is multiplied with B. So you have this term. Okay. And you can, I have done directly. Otherwise, you can do by LHS and RHS. So here I have actually separated. Otherwise, you can do right like this, and then you can solve for this RHS part. Means you can do C1 alpha plus C2 alpha. So comma B, C1, sorry, so A comma B. Just think about C1 A comma C1 B plus C2 A comma C2 B. Now if you add, so you have C1 plus C2 A comma C1 plus C2 B. So you have this, which is already there. So, okay. So you can uh, find that both LHS and RHS are equal. So this 10th axiom, 10th property is also satisfied. This means R2 is a vector space. So are you getting this? Actually, the in vector space, the flavor is completely different. Mainly when you are checking for vector space, mainly that. And after this, you will there the concept, the topics are interesting when you will check for subspace or linear transformation and linear dependence. That is interesting. Okay, interesting means there will you will use rank or other concepts, so it will be little easy. But here you have to do all 10. You have to check all 10 exams, so it takes time and flavor is something different. So, but you must have patience to understand and listen for this. Yes, 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 Shiva. So I have taken one more example. Whenever we have space of all 2 cross 2 matrices. Okay, so M2R is what here? It is a set of all 2 cross 2 matrices. Okay, so when you have set of all 2 cross 2 matrices and it is saying under matrix addition, you know matrix addition, I have already teach you about how to add two matrices. You already know. I have already taught you about this. And scalar multiplication, you also know how to add two matrix, how to multiply by a scalar in a matrix. When you have to multiply by a scalar alpha in the matrix, so alpha is multiplied in each element. So it is saying that if you have a set of 2 cross 2 matrices, okay, and you have matrix addition as scalar multiplication of matrices as two operations, then it is a vector space. So see, when you study in physics or other places vectors, so now that we are generalizing for matrices of order 2 cross 2, or we can also do this for a matrices of order n cross n. So now the elements are here matrices. Okay, in previous example, the elements were ordered pairs in R2. Okay, now here we have matrices. So how to check under vector addition? First, you have to check for closure law. So according to this closure law, you have to add two elements. Now the already A, B, C, D, alpha is used in this question. So that is why I have chosen symbol XY. Okay. Suppose this matrix is X, this is Y, and this is Z. So I have taken X, Y, Z in place of alpha, beta, gamma. So for closure law, you have to check closure means the sum or addition of two will be a vector. Okay. Addition of two vector will be a vector. So X means vector is this matrix. Y means another vector. Vector means matrix. Okay. So these are two cross two matrices. If you add these two, then again you have a matrix of 2 cross 2. Okay. So this belongs to M2R. M2R means matrices of order 2 cross 2. R means scalars, these elements are from R, real numbers. Now, associative law. If you add first y and z matrix, then add x, or if you do addition like this, x plus y first, then z, then you will see that both are same. Okay, so associative law is satisfied. Then existence of identity. If you have matrix X, which is ABCD, okay, so which matrix is to be added so that you get the same matrix again? So this is the zero matrix having all entries zero. Okay, so zero matrix is actually what, zero vector or identity matrix or identity vector. Okay, now existence of inverse. So which matrix is to be added in this matrix X so that you get zero matrix? So X is this ABCD matrix. So if you add this matrix having negative X minus A minus B minus C minus D, if you add these two, so you get zero vector, zero matrix. Okay, so this means that each for every matrix, because ABCD is taken by, because any arbitrary matrix of order 2, ABCD can be any number. So this means that for every 2 cross 2 matrix there is an inverse for that matrix, and addition of that matrix gives zero matrix. Okay, then commutative law means if you add two matrices X and Y, or you add Y plus X, both have same value. Okay, so order does not change the value, order does not matter. So X plus Y is same as Y plus X. Okay, so these axioms hold here for vector addition in case of this example of matrices. Now to talk about the scalar multiplication. First, we multiply by this symbol, because we have already taken in this matrix X. So C1x is what? C1x is multiplication of C1 in each element of matrix X. We have this matrix. Again, this is a matrix. So it is belongs to X. Okay, then 1 into X. 1 means real scalar. So 1x. When you will multiply by 1 in X, you again have. Okay. Then C1, C2x. C1, C2 is a scalar. And X is matrix. When you multiply in this, you have this matrix. And you have to show that this is equal to C1 into C2x. So you can find this C2x, then multiply by C1, you will have same value. I have done directly, but you can find LHS and RHS, and you will see that both are same. Then in next, you have C1x plus C1x plus y. So I have added x plus y and multiplied with C1. So you have this matrix. Fill this. Okay. And what you can do, I have directly got this C1x plus C1y from this, or you can do what? You can multiply by C1 in x, then you can multiply by C1 in y, and you can add them. Then you will see that this is also equal to this. Okay. Then 10th axiom is C1 plus C2x. Means you add two scalars and multiply it in vector. So C1 plus C2x is also equal to C1x plus C2x. So you can separately evaluate LHS and RHS and show the equality of both. So in this way, we can say that M2, the set of all 2 cross 2 matrices over real numbers, it's a vector. Is it clear to all? Is it clear? Okay. What about you, Sairam? What about Arnav? Okay. Sairam, are you getting? Okay. Uh, let's discuss another example. Now, in this, you have to show that R cross R means R square. Okay, Sairam, no problem. You can listen, and but the further topics after this means about, as I already told you about linear dependence and subspaces, or when you I'll tell about eigenvalues. So these might be little bit easier for you. Okay, so listen it. It's good, and you must also try to solve after the class. Okay, so it will be helpful for you. See, in the next question, you have to show that r square with usual addition and scalar multiplication. With this, see, in example one, I discussed with you about r square, but there the addition, the usual addition was this x1 comma y1 plus x2 comma y2, which is nothing but x1 plus x2 comma y1 plus y2. This is called as usual addition, and we did for this. Okay, and there in that question, scalar multiplication was alpha time x comma y is alpha x comma alpha y, and we know that with these two operations r square is a vector space. Okay, in example first we discussed about this, but in this example 3, here the addition is usual, means this one same, but scalar multiplication is changed. Now it is defined as alpha times a comma b equal to 0 comma alpha b. Okay, and you have to check that it is not a vector space. So I want to say that addition is same usual, and the scalar multiplication is changed. Okay, so we can only check for the axioms of scalar multiplication, not for all, because there are 10 axioms to be checked for a vector space, but for a vector space, for a space to be not to be a vector space, not to be a vector space, we have to show that if only one axiom is not satisfied, then it is not a vector space. Okay, but question is, uh, for which operation we must check first. So I want to say that here the scalar multiplication is not usual, it is changed. So that is why we must check for the axioms under scalar multiplication. Okay, so first axiom was for this, c alpha must belongs to b, c is a scalar and alpha is a vector. So now I have taken, in this question actually alpha is taken and alpha is scalar, so I have taken here actually for c is alpha in this example, and the vector alpha is taken as a comma b, so don't confuse with the symbols. Here it is scalar and alpha a comma b is a vector, so don't be confused with the symbols. Now alpha into a comma b is what, according to the definition given in the question, it is 0 comma alpha b, it is belonging to r square. R cross r means r square. Okay, so this is okay, because first axiom says that c comma alpha belongs to b, so we have this. Now second one is that 1 into alpha is alpha. If you multiply by 1 in a vector, we must have that vector. But in this vector is a comma b, 1 is 1 scalar. Now if I multiply by this one in a comma b, what happens? What happens? So we have to multiply according to the given rule. Given rule is saying that when you are multiply by alpha, when you multiply by alpha in a comma b, so first entry will be, first component will be 0, another will be alpha b. So that is why by using this definition, when you multiply by 1 in a comma b, you have first element 0 and second element is alpha into b, means 1 into b. So this is 1b and b. So this means this is 0 comma b. This is 0 comma b. Okay, so just a minute. Yes. So it is 0 comma b. And according to this property, the property says 1 into alpha is must be equal to alpha. But it is now not equal to this a comma b. See here, 1 dot a comma b is equals to 0 comma b which is not equal to A comma B. But according to the axiom, we must have 1 into alpha equal to alpha. So this A comma B is different from this 0 comma B. Okay. So this is not equal to A comma B. This means that it is not satisfying this second axiom. So it is not a vector space. Are you getting this? Okay, Arnab. Next one is, this is again for R cross R. For R cross R, usual addition is there. Now again, multiplication is changed. Scalar multiplication is changed here. So here alpha x into x comma y is alpha x comma alpha square y. So you have to check the axioms for scalar multiplication. Okay. So I have checked. The first one is satisfied. Second, third, fourth. These are satisfied. See here, for fifth one. This is not satisfied. Why? In the fifth one, we have C1 plus C2A, and we have to show that if it is, we have to check that whether it is equal to C1A plus C2A. Okay. So in LHS, C1 plus C2A means element of vector space, which is taken as x comma y. Okay. So when you will apply, multiply by this C1 plus C2 in x comma y, what do you have? C1 plus C2x and C1 plus C2 square y, whole square y. Why? See the definition. According to the definition, what do you have when you multiply by alpha? So alpha is multiplied in x. That's okay. But alpha square is multiplied in y. So when I am multiplying by C1 plus C2, so C1 plus C2 is multiplied in x. That's fine. But C1 plus C2 whole square will be multiplied in y. Okay. So okay. So when this square is opened, so you have this. Now, if I take RHS part, C1A plus C2B, C1A means C1x comma y, C2A means C2x comma y. When I multiply by C1 in x comma y, so this is C1x comma C1 square y. Okay, because C1 will be multiplied in x and C1 square is multiplied in y. Similarly, for C2x comma y, you have C2x comma C2 square y. Now, if you add these two ordered pairs, you have C1 plus C2x, comma C1 square plus C2 square y. So this is your RHS part. This was your for this was this LHS part. So these two are not. Why? In LHS part, you have additional term 2C1 C2, which is not here in RHS term. Okay. So if this axiom is not satisfying here. This is why this is not a vector space. Or you can, I have checked first four exam, then fifth is not satisfying here. You can do directly. Roughly, you can check the others and you can do this fifth one. Okay. But for teaching purpose, I want that you must know everything. That is why I have shown every axioms that these four are satisfied and fifth one is not satisfied. Okay. So R cross R is not a vector space. It's okay. So there's one more example is there. I'm not going to discuss that. Let's discuss this sixth one. You have to show that the set of all rational numbers, you know, the set of rational numbers, which is denoted by Q, is over R. Over R means scalars are taken from reals. So scalars are taken from reals means scalars can be rational or irrational. Okay. Not a vector space. You have to show that. So I have only checked the condition C alpha. Means first condition of first axiom of scalar multiplication. So we know that if C belongs to field and alpha belongs to vector space, C alpha must belongs to V. This was the first axiom of scalar multiplication. So I have taken C equal to root 2. Okay. Not belongs to Q. can have R or rational or Q complement. So I have taken C equal to root 2, alpha equal to 3. Okay. So we will see that root 2 into 3 means 3 root 2. So 3 root 2 is not belonging to V. Actually here V is what? V is your Q. F is your R. Okay. So F is R. So real F is R. Field is R. So we have to take scalar means C from R. Okay. C from the field. So I have taken C as root 2 and alpha as 3, which belongs to this vector space Q. This is set Q. Then C into alpha is this, which is 3 root 2. That does not belongs to Q. And according to the axiom, C alpha must belongs to V. But here C alpha is not belonging to V. Why? V is Q. So C alpha is a irrational number. It is not a rational number. So it is not belonging to Q. So Q is not a vector space over R. Okay, because we are multiplying with scalars which are not rational number, which are irrational, and irrational into rational will give you irrational. So that is not a rational number. So it is not a vector space. So is this clear to all? I have discussed a little about some vector space and some examples based on vector space. So for having a vector space, all 10 axioms must be satisfied. For not having vector space, if any one axiom is not satisfied, then it is not a vector space. Is it clear? Okay, Arnab. Now, what about vector subspace? What about vector subspace? See, um, if you have a vector space V, vector space mean if it is a vector space V, this means there will be some vector addition and there will be some scalar multiplication over some field F. Okay, so this set V will satisfy 10 axioms. Okay, this if it is a vector space. Now, if I take some subset of this, if suppose this is a W, if it is a subset of V is a set which satisfy axioms under these operations, so that becomes a vector space. But now, if I take some subset, some part of that V, okay, and if it is again satisfying all these axioms under the same operations of V. If it is again satisfying all those 10 axioms under the same operation of V, then it is again a vector space. Then it is okay. Then W will again as a vector space. But since this W is lying inside V, this W is subset of V. That is why we called it as subspace. Subspace means sub word is there because it is subset. So see here in the definition, if V is a vector space over the field F and W is a subset of V, which is non-empty. Okay. And then if V is a vector space over F under the same operations of V, then V is called as subspace of V. So you have V, you have this W is a subset of V, but if V is a vector space